Hey grade 8s, this is Science 8 Unit 3. The final part of the unit, we're going to call this pressure. I encourage you to read our textbook, the Pearson Saskatchewan Science 8, page 236 to 257 for more information. So let's talk about this. We're going to talk about a bunch of different types of devices that use this concept of pressure. But first, it might be a good idea to kind of figure out what pressure is. So pressure is the amount of force applied on a particular area, okay? So the amount of force on an area. So, for example, if I push against this pencil, I'm applying a force to it, and the area would be the amount of this fingertip and the pencil that would be in contact with it, okay? So if I have a force and an area that force is applied to, I can calculate the pressure. If you think about it this way, pressure, it's equal to the force divided by the area that force is applied to. And if we think about it, force is measured in newtons. Okay, that's the measurement of force. And the area, it could be meters squared, and this is the most common unit that's used, is newtons per meter squared. If you think about area, it's the length times width, right? For a rectangle, but sometimes there's more complicated formulas. For a triangle, you need to divide it by 2, the length times width. For a circle, you have pi to deal with. Now, scientists, they've come up with another unit that is used that means the same thing as this, and it's simply just pascals. Okay, so 1 pascal would be 1 newton per meter squared. For example, you might have been inflating a tire, and you measure a certain amount of kilopascals that fit into it. We'll look at a few examples as we go. All right, I'm outside here and realized my hair did not hold up this morning, but I just want to talk about one device. There's something right here. These are snowshoes, and we're going to talk about what these actually do for a person and why someone would wear snowshoes. A little history. It's estimated that snowshoes were used in Central Asia about 4,000 to 6,000 years ago. Many different other types of devices were used by the First Nations people in North America a couple thousand years ago, and or up to a couple thousand years ago, and they're really useful. I know some of you guys have probably walked in some deep snow, and as you're walking along, your foot goes onto the snow, and then it sinks through the snow, and then you take another step and it sinks in, and then you're supposed to step up out of it, and it's almost like you're doing high steps the whole way, right? So snowshoes enable something to happen. Snowshoes are put on your feet like so. You put your foot under here and you put the strap behind. I'm wearing flip-flops and socks just because I know it annoys some people. But as you step, it's a bigger area, right? What's the difference between the bottom of your foot and a snowshoe? It's substantially bigger. It spreads out the area. And that ends up causing the pressure to be less. I'm going to go back and use a piece of paper to describe this. But first, let's just think about this. This will keep you up above the snow because there's not as much pressure, which is what causes your foot to go through. It'll stay above. Okay, I'm going to give an example here to explain why a snowshoe would change the amount of pressure. Okay, so I know these numbers won't quite make sense, but let's pretend that there's someone's foot and the area of that is 1 meter squared. But if they put on a snowshoe, the area of that would be 5 meters squared. Okay, so let's compare with no snowshoe is scenario 1, and with the snowshoe is scenario 2. Now, their weight would be the same, which would mean their force that they're pushing down into the earth on average would stay the same. So if it's staying the same, that force on average would stay the same. The force stays consistent. It doesn't matter what it is, but let's say that their force is, okay, and so this person, their weight would be, let's say it's 500 newtons, okay? This, just for those who are wondering, on Earth here, it's 500 newtons is approximately equal to 112 pounds, okay? So 112 pounds, so I don't know, that might be around an average grade 7 or 8. I have no concept of weight anymore. It's been a while since I weighed that. Anyways, so that's what this force is. That's a force that's being applied down onto the ground with footsteps. So if we think about this, and this is an average, not every step down is going to be the same. Sometimes it's really forced down, other times it's lighter. But the average step, it would be similar steps for both of these. If we want to calculate our pressure is going to equal our force divided by area, okay? So let's look at this. Our pressure is going to be our force, 500 newtons, divided by our area, which is 1 meter squared, okay? So in this first case, our first pressure would be 500 divided by 1 is 500 newtons per meter squared, also known as 500 pascals. Okay, what about with the snowshoe? Notice something. It's still going to be force divided by area. It's just we're going to use the force and area that applies to the situation. Force is 500 newtons divided by area is now 5 meters squared. Okay, notice the number got bigger, the area got bigger, but notice it's on the bottom of the fraction, which means we're dividing by it. We're dividing it into more groups. If you think about division that way, it's more groups, which means each group's going to have less. 500 divided by 5 is 100 newtons per meter squared, which also you could have written 100 pascals is the unit that scientists use, so they don't have to write as much. Plus Blaise Pascal, who it's named after, was an awesome mathematician. He also has the name Blaise, which I think is super cool. I digress. So if we compare this, notice that the smaller the force, smaller the area, smaller area means a greater pressure. Greater area means a smaller pressure. Smaller pressure, greater pressure. So with any formula, so if we take a formula, whatever's on the top of a formula, if it gets bigger, it's going to make the other thing on the other side of the equation bigger. The thing that's on the bottom, if it gets bigger, it's going to do the opposite. It's called inverse. It's going to cause this to be smaller. So notice bigger area, smaller pressure. Smaller area, bigger pressure. And that's how snowshoes work, is they cause the area to be bigger. The force stays the same, the area is bigger, and because there is a smaller pressure, it's less likely to get through. I'm gonna do another illustration here. All right, I have here a bucket of water and a card. And now I wanted to illustrate this pressure idea. There are other scientific concepts that this would apply to the situation, but pressure is one of them. So there's the surface of the water here. Now let's pretend that I'm going to take this card and I'm going to set it down flat like this. Okay, I'm going to set it on the water flat. Will it sink or will it float? Well, let's figure this out. Let's just set it down. Oh, look at that, it floats. Okay. So the card floated, and now if you think about it, what would the area be? Well, the area would be the width, and the length, and you multiply them and you could calculate the area. We'll do that after I do the little experiment. Because this is the surface that was touching the water, right? So that's the area that matters when calculating pressure. It's the area of the contact, right? Now, what if I were to use, this small edge? Its width is almost 0. It's really tiny, maybe a millimeter. And the length, whatever that is, maybe 5 centimeters. What if I stuck it this way? You'll notice it goes straight into the water there, right? It pierced straight through the surface of the water. Why would it pierce through? Well, it's because the pressure is higher, because the area is smaller. So I have a playing card here that I was using. Let's just measure it. Okay, it looks like the width is 63. So width equals 63 millimeters. What's the length? This length here is 88 millimeters. And what's the thickness? Well, it's not even half a millimeter, but let's pretend it's half a millimeter. Okay, it's not even that. But the thickness is 0.5 millimeters. Okay, now let's look at our two scenarios. This is a different question, so I should cross that off. Okay, scenario 1 was when we were setting it flat, which means the surface was this surface, right? So the whole area of this would have been this, which we called width, and the length. So width and length. So the width is 63 millimeters. The length is 88 millimeters in this case. But because we want to get our unit in pascals, and this is in meters squared, before we multiply it, we should convert these to meters. 63 millimeters, we know, is 6.3 centimeters, and 6.3 centimeters is 0.063 meters, okay? And this would be 0.8088 meters, okay? We're going to use those to multiply, right? So the area equals width times length, right? So let's get our width, 0.063 times 0.088 meters. Let's do some multiplication. I put the 88 on the bottom so that I would have the same digits twice, just with a 0 added. Made it go a little faster. Okay, and how many decimals? 1, 2, 3, 4, 5, 6. So it's 1, 2, 3, 4, 5, 6, and that's where it is. So the area is 0.005544 meters squared. So I just went and found the weight of this card on a little scale, and I found out that it was, to save a little bit of time here, it was 0.04 ounces, which happens to equal 0.0025 pounds, which happens to equal 0.01112, so forth, newtons. Okay, so we're going to use this as our newtons. Okay, 4 non-zero digits, 4 non-zero digits. That's the only reason I chose that many. So if we know then that is our force, right? Our force down that this card was applying to the water. So then we know our pressure is going to be 0.01112 newtons divided by 0.005544 meters squared. And we're going to end up with our pressure. And when we do that math, we end up with 2.006 pascals, or newtons per meter square, whichever you write. So that's the pressure that we had when the card was flat. Now let's do scenario 2, that second one we did, where the card was, what was the width? Well, it was still the width. It was still that 63 millimeters, which is still 0.063 meters. And the thickness was our length that we'd multiply by, right? So area equals width times thickness in this case, which we said was approximately 0.5 millimeters, right? Which is 0.005 meters. Okay, so let's multiply these. I'm going to do it on the side here. 0.063 times 0.005. 5 times 3 is 15. 5 times 6 is 30, 31. And then we move 3. 3 is 6. So there would be 6 decimal places. So our area is 0.000315 meters squared. And our force is still the same. It's the same card, right? Our force is still 0.01112 newtons. So let's calculate our pressure. We'll go 0.000315 meters squared divided by 0.01112 newtons. Did anyone catch my mistake? These should be opposites. It's force on the top, right? I wish I could say I was just testing you guys. I actually just made that mistake. Sorry about that. Good thing I caught it before I went too far. Why? Because the formula for pressure is force divided by area, surface area. So force goes on top, area goes on the bottom. Okay, so let's calculate that. And when we do, we end up with 35.30 pascals. Compare these. 2 compared to 35. 35 is much greater, right? So when the card went in this way, the surface area was a whole lot less that was making contact with water, which means the pressure was a lot more. There's a greater pressure. Much greater pressure means that it's able to pierce through the water. Yes, there's other scientific concepts that apply to this situation, but it illustrates this idea of pressure. It's the same reason why snowshoes keep you above the snow and your feet don't sink in. If you look at animals, for example, that live in snowy climates, they usually have much wider hoofs than others, and they'll have extra surface area so that they don't fall through the snow. It gives them that advantage, and they're able to survive in those harsher climates. As you guys probably remember from last year, we talked about something called particle theory. You know, in a solid as pictured here, it's very rigid. All the particles are much closer together. And as there's more energy put into it, they start to vibrate more and they want to move around a little more and they turn into something maybe liquidy. So here we've got solid around the outside and liquid. They're able to flow a little bit more away from each other. And they're sliding over each other. And if you keep adding energy, eventually they might turn into a gas. Okay, and the particles are able to move all over the place. Now, you guys might have noticed, for example, a pop bottle or a soccer ball or something like a tire. In the cold, it deflates a little bit and it's a little bit flat. And in the warm air, it expands. For example, right here, I have a soccer ball that I've just taken out of my freezer a little bit ago. And you're going to notice that it's pretty squishy, right? It's lost some of its pressure, but as this warms up, it's actually filling up a little more. And there's a little more pressure. It's because of these particles. As heat is removed, so it started maybe like this and it was a full soccer ball. It was pretty full. I pumped it up. It started with particles. They have more energy and they started becoming a little more compressed. So the volume that they took up was a little less. What ended up happening is there's a little less pressure, which means when I apply pressure on the outside of the soccer ball, as I apply pressure on the outside of the soccer ball, it's able to overcome the pressure that's pushing out from the inside of the soccer ball. So just to illustrate this, I've drawn a soccer ball here. Yes, I know it's not perfect. There, that's better. So there's all these little particles inside the soccer ball. They're moving around. They have energy. And all these particles, they want to spread out, right? They have lots of energy. It would be like, you know, an overcrowded shopping mall. You kind of try to, on a Black Friday, you try to get into your own space, try to stay away from people as much as possible. to get to your thing so you can move quickly. But all of these are pressing outwards on this soccer ball. And the material that the ball is made out of is able to withstand a certain amount of pressure. And it tries to equalize that pressure, okay? So the pressure that's on each of those, the area, the surface area of the inside of the soccer ball, it's going to be somewhat equal, okay? Pretty close anyways. And all these little particles, they're pushing around, bumping around, and they're causing that ball to be inflated. And if I were to pump this more, which I'll show you. So I have this ball pump. I'm pushing it in, okay? There's a little piston that pushes, and this is pushing air into the ball. This ball is filling with air, okay? And it becomes a lot more rigid. It's able to push outwards, okay? I'm pushing more particles into the ball, air particles, oxygen, nitrogen, maybe some carbon dioxide, who knows? And this ball has now become a whole lot firmer. Okay, the pressure inside this ball is a lot less. I meant to say more, it's a whole lot more. More pressure, more particles, more pressure. But now, let's say I take this. I was getting ahead of myself, I was thinking about this. I'm going to let some of these particles out. I'm going to let this leak for a bit. Notice that the particles, they go to where there's the least resistance. Where's the least resistance? Where there's this hole that it can pass through, okay? And as this goes, it deflates, okay? There's not much pressure, and so the atmospheric pressure, the pressure outside the ball, the pressure of the air outside is then able to push against it and is able to cause those little ripples and push down. I can also push in with even more than what the atmospheric pressure is, and it will become even less as particles go out. Now listen to this. I'm going to push out, and then I'm going to let go. Notice that it starts filling up. That has to do with the force of this ball wanting to return to its natural shape. And as that edge that's inwards wants to move this way, it's pulling this way, it ends up sucking air in through wherever that hole is, okay? So it sucks air and particles move back into the ball. My camera got rotated there, I'm sorry. So if there is a hole in a system, so it's not a closed system, but it's open, okay? There's an opening. What's going to happen is the pressure out here and the pressure inside are going to try to equalize. They're going to try to be the equal pressure. And how it does that more often than not is moving particles or changing the volume. So the amount of volume might change, or the particles will actually move through. So when I was squeezing the ball and then letting it re-inflate, it was particles moving in and out. It was also the volume was shrinking. Now I want to show you something. You'll study this in high school if you take chemistry or physics, or even in university as well. This thing's called the ideal gas law. And I'm going to just write in some things here. There's pressure, volume, which is like that amount of space. There's the number of particles. Let's just do this so it stays on the screen. This is a constant. We won't worry about that. Sorry, usually use a K for constant, but it's actually spelled with a C. And then you have temperature. And scientists have discovered this, and I just want to point out that in order for this to be equal, so these two multiplied by each other and these three things multiplied by each other, for them to stay equal, if you change any one of these, something else has to change. For example, if you raise the pressure, you pressurize it more, maybe by putting in more particles, it can stay equal. But if you don't put in more particles, so you close the system, you close it, not more particles are going into the ball, let's say, but you want the pressure to go up, this thing it's multiplying by has to become less. Okay, so on the same side of the equation, if one thing increases, the other has to become less if the other side is staying the same. Or if I raise the temperature, but the pressure and the volume are going to stay the same, I'm going to raise the temperature, something's going to have to happen where we somehow lose particles somehow if these are going to stay the same. But that's really hard to do. But this is called the ideal gas law, and it says that the pressure times the volume is going to equal to the number of particles times some constant for the type of substance it is times the temperature. So if you raise temperature, either the volume or the pressure will need to go up for it to stay the same, or else you might get some sort of burst or something, explosion. That's just for the eager students. You could look up more about the ideal gas law if you're interested. There's lots of great YouTube videos on it, but that's just for the keeners, that part. There's an example in your textbook on page 242 of a soccer ball getting kicked. Okay? Now, when a soccer ball gets kicked, what's changed? Well, the volume of it has been changed. The volume gets smaller. So the volume went down, right? The volume went down. Did any particles leave the soccer ball? Are there less particles? No, it's the same. It's still the same substance that's in the soccer ball. The temperature probably didn't change. You know, there's not a fire underneath that. Maybe that person's foot is fire, but who knows? So what has to happen if volume's going down and these are staying the same, pressure has to go up. And in fact, the pressure in the ball, because of that, there's more particles, the same amount of particles in there, but they have less space to move. There's more collisions, bumps, and all that sort of stuff. So that soccer ball that gets kicked, that ball that gets kicked and has that, foot hitting into it, it's going to have lots of pressure, and what happens is that extra pressure pushes back and causes that ball to fly off and bounce off. This is called compressibility. So fluids can compress, okay? They can be under compression. So compressibility or compression is when a force is applied to an object. Okay, so different things can be compressed. They can be squeezed together or they can expand, okay? So you can compress air, you can compress liquids, you can squish them, or you can cause them to expand a little bit. Now, gases compress more. Than liquids, I meant to say. Liquids. Things that are compressed tend to change shape unless they're in a very rigid container, like a compressed air tank won't. However, if there is a little part in it that kind of gets thinner, maybe the pressure might be able to break through it. So here's a bottle. What I'm going to do is I'm going to increase the pressure inside it by twisting it up, okay? I'm going to twist it up. I've also decreased the volume. You'll notice that it's shrunk quite a bit. Okay? If you listen carefully, I was actually able to cause there to be a little bit of a leak through the lid because that's the path of least resistance. It's the least resistance against it, and the air tried to escape. And now, if I slowly loosen this bottle cap, it's going to go flying. No. Why? I was too slow. Air was able to release out of it. But if I try again and I make it really nice and compressed, and I go quickly, and I'm going to switch hands because I'm better at it with the other hand. I can cause the pressure to be released and that bottle cap goes flying. Now you'll notice there's kind of a boiling sound in here. And that's because temperature does have a relation to the pressure and the volume. So in that bottle, I ended up twisting it somewhere around here and basically getting rid of all of this bottle right here. You know, some of this was still filled with some particles, but even if so, this part in the side and this part in the side here had been reduced. It was compressed. So some of the air particles that would have filled this volume were now in here. There was an extra amount of particles in the same volume. So more particles, increase that. It means one of these has to go up. And the volume was going down, which means pressure had to go up quite a bit. And because of that, it made it so that I'd need more pressure if I wanted to try to dent this. If I pushed into the side, I wasn't able to compress it because there was a greater force out caused by this pressure. But then when I changed this closed system to be an open system, and I did it quickly, that pressure quickly pushed those particles, they moved, they pressed this way and caused that bottle cap to go flying. Now, this little bubbling that was happening and the steam that was happening, that's because I had left, there was a little bit of water particles in here. Okay, and as they got compressed and compressed, some of these gas particles that were in here, they got pressed and they got forced together and became a little bit more water. And then when the pressure was released, so the pressure went down, some of those particles changed. The volume got much greater because it was a great volume out here, and it ended up causing some of these particles that got compressed into liquid to turn back into gas particles. But that's not the main point. That's, you know, high school chemistry. You can wait if that's confusing. But the increase of pressure was because I was able to compress this bottle and make pressure inside it, and it's able to shoot the cap off, which is cool. Don't aim it at anyone if you do try that. And make sure everyone's wearing safety goggles. So just to recap some of these things, pressure equals force divided by surface area. Okay. That is the big formula to know. And so that means newtons per meter squared, or pascals is the other one, is the unit for pressure. Gases and liquids can be compressed. Gases can be compressed more than liquids. Solids can't really be compressed because they are already in that shape that's the smallest. Now, ones that seem to be compressed, it's because there's different formations that some can be done. And there's various technologies that use this idea that you increase the surface area. For example, snowshoes, you increase that surface area and you can deviate the pressure. I did want to mention one thing. If we think about it, the amount of weight that's pressing down under something this big, let's say each of these is 1 Newton, compared to this big, if this one spot that's being pressed down on has to deal with these 4, it's a lot more difficult if, you know, they just have to deal with 1 each, right? So that's another way to look at this.